Welcome to qnawire.
Alright, let's go ahead and start solving this problem. So the question is, find the heat outflow, so it's an outflow this time, not an inflow. The heat outflow on through a sphere with radius r, where the temperature is inversely proportional to the distance from the center. So I will arbitrarily just choose the center to be located at the origin. So any point x comma y comma z would be giving us the distance from the center as the square root of x squared plus y squared plus z squared. So using that, we can actually deduce what um, u and s are going to be. So u, we're going to start with that. It is going to be inversely proportional. So it is going to be a constant divided by, I don't like that straight line. Uh, there you go. Divided by the square root of x squared plus y squared plus z squared. Okay, now normally I use k for the constant here. That's just the way I've learned, but k, because this is related to heat flow, I want k to be on conductivity. And we are not given what that is, but it's still a constant, so we're going to let this be our conductivity. Okay, now we just need the equation of the sphere. We know that very well. X squared plus y squared plus z squared equals 2a squared, because the radius is given to us as a. Okay, so using this, we're going to try to figure out what the general form of the heat flow is going to be. So let me put this over here. Right. Similar to the previous problem, we're simply going to we're going to figure out the flux F dot n ds, which we also know that this is equal to the same integral, but negative k del u dot n ds. Okay, all right. So we already have negative k del u. Now, one of the things that we have to do here is we have to be very careful that because we have x squared plus y squared plus z squared is equal to a squared, which is a constant, I don't want you to think that you can simply just substitute that in freely when we take derivatives and stuff. So we have to take the derivative with respect to the variables first, and then later substitute the a's in to figure out if it actually simplifies to something nice. So it's one of the things that we have to be careful about. Anyhow, del u, we're simply going to take the derivative where the expression x squared plus y squared plus z squared is inside the square root, so I'm going to call that to the 1/2 power. It's inversely proportional, so it's going to be negative 1/2. C is a constant, so I'm going to deal with that later. Let me call that, let's see, what's not a confusing variable? Let's say x, for example, large x. Okay, I do statistics, so I'm more used to using this for random variables, but just for simple purposes. Now, I'm going to say large x prime. It's basically the partial derivative with respect to x. This is going to take the form negative 1 over 2 x squared plus y squared plus z squared to the negative 3 over 2. do this with the power rule, but the chain rule tells you you will have, you'll be multiplying the derivative of the inside with respect to x, so you will have to multiply 2x. Y and z are independent from x, so we do not need to worry about that. And this simplifies to negative x squared plus y squared plus z squared. Now, we know that x squared plus y squared plus z squared is equal to x squared, and this is where we can actually substitute it in. Not x squared, this is a squared. So if we substitute that in, this simplifies to negative x times a to the negative 3. Okay, it cancels out with the fraction portion of the exponent. And I took it with respect to x, but the y squared and the z squared behave exactly the same way. So the partial derivative with respect to y and the same thing with respect to z is going to have a very similar form that looks like that. And as you can see, negative a to the negative 3 power is just a constant, so we can pull that out. So let me organize this information a little bit. Measure here. Oh, there you go. So finally, when I calculate del u, using similar processes 2 more times, you can calculate that. This will simply be, I wrote it down somewhere, hold on. Negative a to the negative 3 x comma y comma z. There you go. Now n, the normal vector. We've seen it in the examples, and we've also seen it multiple times whenever we deal with spheres from chapter 15 or 16. The normal vector is simply going to be 1 over a of x comma y comma z. And of course, if you parameterize the expression, you should be able to deduce this, but that's going to take quite a while to get there. And since it's quite a simple fact to memorize, it's not that difficult to remember, and we're just simply going to use this one. So let's call that a to the negative 1, x comma y comma z. Okay, so f dot n simplifies significantly here. This is equal to, let's recall, it is negative k del u dot n. And then we know that we're going to get a term x squared plus y squared plus z squared, which we know that it's equal to a squared. So we can use that fact over here. So this simplifies to, like that, it is going to be kca to the negative 2. Where did that c come from, you might ask? Let's recall. Oh, I must have not included in here. Oh, I see. Hold on. U is inversely proportional to the distance from the center, And because we are not given what that constant is equal to, it's simply the value that I didn't use, but it just comes out of the vector, so you can just put it right there. Okay. All right, so moving on. kCa to the negative 2 is what f dot n is equal to. And finally, if we want to figure out what the heat flow is going to be, we can pull out all of these constants outside the expression. So you will get kCa to the negative 2 times the double integral through s ds. And as we know, this expression is simply the surface area of, in this case, the sphere. And then we know that it is equal to 4 pi r squared. The radius is equal to a, so this is equal to 4 pi a squared. Now, what's really interesting, at least in my opinion, is the fact that because the a's cancel each other, when it comes to heat flow through a sphere where the temperature is inversely proportional to the distance from the center, it turns out that the radius of the sphere is independent from the heat flow. So I thought that was really interesting. Anyhow, this simplifies to 4 kc pi, and that is going to be the outflow, which is the answer, and that's how you solve these kind of problems.